let's briefly discuss the central limit theorem, what it is, what it means, and do a quick example of using it. So the central limit theorem is like the fundamental theorem of statistics. It's really the result that makes a lot of statistics work. So what it says is if you take any random variable, let's call it capital X, with mean mu and standard deviation sigma. Now remember, random variables don't have to have a mean or a standard deviation, because the mean and the standard deviation for a discrete random variable, those are defined by sums, which could be infinite and which could diverge. And for a continuous random variable, they're defined by integrals, improper integrals, which could also diverge. So the central limit theorem only applies to random variables x whose mean and standard deviation exist. And another way of saying that is that the expected value, that's the mean, of x exists, and the expected value of x squared also exists. Because remember that you can get the variance by doing the expected value of x squared minus the expected value of x squared. And so if both these things exist, then you do this one minus the square of that one, and you'll get the variance, and you square root it, you get the standard deviation. So if both these exist, that's a sufficient condition for the mean and the standard deviation to exist, and so the central limit theorem applies. So that's the only thing you need to be true about a random variable for the central limit theorem to apply. If that's true, then you define a new random variable x bar by taking a simple random sample from the distribution of x and taking the sample mean, the average. That's what I'm doing here. So I'm taking x1, x2, xn. These are all values drawn from the distribution of x independently, and I'm summing them up and dividing by n, the number of values in the sum. So I'm taking the average of a random sample. That's this x bar. The x bar represents the average of a random sample from the distribution of x. Then the expected value of this thing, x bar, the sample average, is mu, which is the same as the expected value of the distribution I was drawing my sample from. So that's what this says. That's also often written in this way. It's also written like this: mu x bar equals mu. So these two are two different ways of writing the same thing. The average value of the sample average is equal to the average value for the distribution you took the sample from. Also, the variance of this guy, x bar, the variance of the average of a sample, is equal to the variance in the population, the variance in x, the distribution I'm drawing from, divided by n, the number of sample values. And that's also written sigma x bar equals sigma over root n. So sigma x bar is the standard deviation of x bar, this guy. And that's the same as the standard deviation of x, it's the distribution I'm drawing from, divided by the square root of the sample size. So I square rooted both things on the right here, yeah, because here I have the variance and here I have standard deviation. So you'll see these two expressions coming up a lot. Those are expressions that are asserting that the average value of this random variable x bar is equal to the average value in the population I took the sample from, and the standard deviation of this quantity x bar is equal to the standard deviation in the distribution I'm taking the sample from, divided by the square root of the sample size. And we prove that, actually, it doesn't take long to prove that, using linearity of expectation here, and using properties of variance here. We proved that when we proved the law of large numbers. So that's all contained in the law of large numbers. The central limit theorem says more than that. It says not only do we have that, we have this amazing fact, which is that not only do I know the expected value, the mean, and the variance of the sample average, I actually know the shape of its distribution, which is really remarkable because I'm not assuming anything about the shape of the distribution my sample came from. So no matter what shape the distribution my sample came from had, the shape of the distribution of x bar, the sampling distribution of the mean, is normal. And its mean is this guy, and its standard deviation is this guy, as n approaches infinity. So as the sample size gets bigger and bigger and bigger, the distribution of this thing, x bar, gets closer and closer to a normal distribution, which is really remarkable and really useful because it means we can do calculations involving the sample mean without actually knowing what the distribution we're sampling from looks like. All we need to know is its mean and its standard deviation. And then we can compute probabilities of getting certain kinds of sample means, that our sample mean ends up in a certain range. So just to sort of graphically illustrate that, what we're saying here is, okay, it wouldn't be surprising if I'm sampling from a normally distributed population. So call this f capital X of little x. So suppose I'm taking a sample from a normal distribution, and then I'm calculating the average of that sample. So I take a sample of values, I compute the average. I take a different sample of values, I compute the average. I take a different sample of values, I compute the average. I keep doing that. And I write down all these averages and I look at the distribution of them. Well, if you think about it for a while, it's not that surprising that what you'll get is another normal distribution. This one's going to be actually narrower than that one was. So this is the distribution of x bar. But the remarkable thing is that even if this distribution is not a normal distribution, I don't actually assume I know anything about its shape. Maybe this distribution is, I don't know, a uniform distribution. And I take a sample from this distribution and I compute its average. I take another sample, compute its average, take another sample, compute its average. Then if my sample size is fairly large enough, the distribution of those sample averages looks normal, despite the fact that this distribution wasn't normal at all. Even if I take a weird asymmetric distribution, maybe like an exponential distribution, like this. I guess an exponential distribution would look something like this. It goes up at 0, and then it comes kind of down like this, like this. All right, even if I take a skewed distribution like this, maybe an exponential distribution, I take a sample, compute its mean, take a different sample, compute its mean, take a different sample, compute its mean, keep track of all the sample means and plot their distribution. It's going to be a normal distribution. It's going to look normal as long as my sample size is big enough. Like I said, this is an amazing result, and a lot of statistics is based on this because it lets us reason probabilistically about the probability that getting a sample with a mean in a certain range without knowing the distribution of the population you're sampling from. All you have to know is the mean and the standard deviation of the population you're sampling from. So let's do an example where we'll do that, do a calculation. So suppose in a certain town, the mean height is 67 inches with standard deviation 4 inches. Question 1. What's the probability that an individual selected at random from this town is taller than 68 inches? And part B, what is the probability that the mean height in a simple random sample of 64 individuals from this town is higher than 68 inches? So in here, I'm just picking someone at random from the town and asking what's the probability they're higher, 68 inches. In this one, I'm picking 64 people from this town, averaging their heights, and asking what's the probability that that sample average comes out to be bigger than 68 inches. So here's the thing. This question right here, part A, it seems easier than this question right here, because here I'm only picking a single person and looking at their height. Here I'm picking 64 people and averaging their height, so more is going on here. It's a more complicated process. You have to pick 64 people and actually take an average. However, this question right here is impossible. I can't do it. Why can't I do it? Because in part A here, what are we looking for? We're looking for the probability x. X is a random variable representing the height of a randomly selected person from this town is bigger than 68. Now, how do I compute the probability x is bigger than 68? Well, I use the PDF of x, which describes its distribution, and I took the PDF of x, and I find the probability it's bigger than 68, so I would integrate it from 68 to infinity. Yeah? But the problem is where's the PDF of x? I don't know it. I don't know what the distribution of x looks like. All I know is its mean and its standard deviation. So I can't compute this. It's just not possible. There's not enough information given in the question. However, in part B, what are we looking for? We're looking for the probability x bar is bigger than 68. Where x bar, that's the average in a sample. But even though I don't know what the distribution of heights in this town is, I do know what the distribution of average heights in samples of size 64 is, because the central limit theorem tells me it's normal. 64 is a pretty big sample size, big enough that the central limit theorem should apply really well. We'll talk about the details of how big is big enough in your sample size later. But in this case, yes, 64 is a pretty big sample size for the purposes of the central limit theorem working out in a situation like this. So I can actually do this calculation. In fact, it's a really quick calculation. I'm looking for the probability x bar is bigger than 68. Okay, wait, before I do. The reason I can do this is by the central limit theorem, x bar is, I'll just say, approximately normal with mean mu x bar and standard deviation sigma x bar, where mu x bar is mu, the mean in the population I'm sampling from, which is what? 67. And sigma x bar equals sigma over root n, which in this case here is sigma, the standard deviation in the population, 4 inches, divided by the square root of the sample size. In this case, 64 is the sample size. And that's 4 over 8, which is 1/2. So, what I'm asking for is the probability x bar is bigger than 68, where x bar is normal with mean 67 and standard deviation 1/2. And so we do this the same way we would with any other normal distribution question. I standardize and I use the z-table. So I'm going to turn this 68 into a z-score with the z-score formula. 68 minus this mean mu x bar, which was 67, divided by the standard deviation, sigma x bar, which is 1/2. And if I compute that, what do I get? 68 minus 67 is 1 divided by 1/2. 1 divided by 1/2 is 2, right? Do the flip-flop and multiply. So, the probability x bar is bigger than 68 is the probability z is bigger than 2, where z is the standard normal random variable. And we can use the z-table to calculate that and do a little drawing. So here's 0. We're looking for the probability z is bigger than 2. That's the area on the right of 2 under the PDF. And using a z-table, we can figure that out. Turns out to be about 0.0228 or 2.3%. So that's the power of the central limit theorem. As long as you know the mean and the standard deviation of the population you're sampling from, and you're asking a question about an average of a random sample, but the probability of getting a certain kind of sample average, right? You can answer that question because the central limit theorem tells you the distribution of sample averages is a normal distribution. You know its mean and you know its standard deviation, so you can do normal distribution calculations exactly as we did before.